Alright, hell yeah. So one of the misconceptions I've always had is that a free-falling bar, the center of mass, let's say in 1 second, is going to travel like 5 meters. So it's going to go from here to here in 1 second. I thought that a hinged bar would also, in 1 second, the center of mass would also travel the same distance because you have the force of gravity kind of acting on all the chunks of mass. So we're going to explore that. And we know that we have this equation, sum of the torques is equal to I alpha. We're going to set that aside for now because what I've been making is videos to show you kind of this relationship but in a linear fashion. So to do that, I'm going to chop up this bar into 2 sections and then say that the mass is located in the center of these sections. Now it's not going to be 100% accurate to the scenario where we just have the total bar hinged, but it's pretty decent. So here I'm going to have a force of gravity on each of these is going to be 1/2 mg because we're saying that the total mass of the bar is split up into both those sections. So this force of gravity is going to be 1/2 mg. Now what we're going to find is that it's the equation for torque alright, how do I say this? Because I'm still learning on the fly too. So it's the torque that actually creates a force upward on this pin. So this pin right here does feel an upward force. And in general, even though if this is free falling, but then I just apply a force. So let's say, yeah, right before this is let go, we have the force of gravity, which would be mg, but then I apply some sort of force here. If I apply the same force, mg, you know what I mean, that same number or quantity, what happens is that the center of mass, because the sum of the forces in the y direction are going to sum to 0, we can say the mass and the acceleration, so the center of mass, its acceleration will be 0 because we would have an mg up minus the mg down. That's going to be 0. We do have the mass of the bar, and its acceleration has to be 0. So the acceleration of the center of mass would be 0 in that case. Now this thing would hella rotate, so that's kind of fascinating. But any force here is going to slow down the acceleration of gravity of that point. So just in general, what we know about this problem, and you know, teachers will do it in class. They'll do this, and then they'll drop that side, and this side will drop faster than gravity. And so if you put a penny there and kind of film it, or you can probably with a yardstick probably be able to do it, but this would fall faster. The penny falls at gravity, and so you do get a separation between those. All right, so let's check out this, and then instead of using some of the torques, in statics, we're just so familiar with forces in the y is equal to mass times acceleration, forces in the x is equal to mass times the acceleration, and then sum of the moments are equal to usually 0, but I'm going to say linearly it's just mass times acceleration times d. Okay, so let's explore that. So we have the sum of the moments about this point is equal to mass acceleration d. Now what we're gonna have to do is we're gonna have to sum, because usually, and a better way to write this technically is sum of the forces is equal to, well, the mass doesn't change, but it's the sum of the accelerations as well. And we're going to take a look at that in a second right here. So moment is force times distance. So for this, let's see how we broke this up. We have L divided by 4. We're going to say this whole bar is a distance L. So we have all these L divided by 4s between these separations. All right, so moment is going to be the force. We're going to have 1/2 mg. That's going to be the force on that. And its distance from the moment is going to be 1/4 L. Now we're going to add it to this one. That's going to be 1/2 mg. The distance is going to be 3/4 L. All right, now we're going to have to add it to this, but we're going to have to kind of do a summation. So this, just in general, is going to be ma1 times d1 plus ma2 times d2. And this will help us learn about what this term is, because what we can do, I'm going to make a few videos on this, because there's a couple ways to get there. You know, this is the one way to get there is just to say, what's the definition of angular acceleration? Angular acceleration is in radians. Radians per second squared. This is a dimensionless term. So if we multiplied by meters, we would get meters per second squared, and that would be acceleration. So that's one way to kind of figure out the equation, is just by using units. So we're going to say that angular acceleration times the radius is just the tangential, or just the acceleration. And we can write this another way. We can say acceleration is angular acceleration times the distance. And that's what we're going to input right into there. So we can say a1 is equal to angular acceleration times the distance to 1. Cool. And we already have the distance to 1. So this becomes, if we substitute this right into there, we're going to have m angular acceleration times d1 squared plus m angular acceleration times d2 squared. Now, this isn't the most obvious. I think the most obvious way to do it is actually, crank out a second, and that's going to be for another video. That's typically what I do, because free fall, hey, we're going to fall 5 meters. Like here, we know that both of these aren't going to fall 5 meters, but due to continuity, when one falls this distance, the other has to fall. And due to, kind of similar triangles, because we have 3 segments to this one. If this one fell 6 meters, this one would fall 2 meters. So let's do both. Actually, let's do both as we go. So, and let's sum this up. This is we have a 1/2 mg term there, a 1/2 mg term there. We have a quarter plus 3/4. So that's just a total of 1L. And so we can take this formula as just 1/2 mgl, and this is going to be the torques due to this bar. And if we just had the original bar at the original center of mass, we would have L over 2, and we would have mg as our force, and times our distance is L over 2, so we would have mg L over 2, which is the same thing as 1/2 mgl. All right. So yeah, and then we're going to use this. But you can see, what did I say the generic term of, well, I made a video before this, and I had to, it just got to be a little bit too much. But this is second moment of inertia. I will go over that, because this term is just kind of the mystery. It's like, what does it mean? What is it? How do you say it? So it's mass moment of inertia. It's just moment of inertia if you're just talking about this. Area moment of inertia is for I-beams. When you're doing structures and you want to know how strong, an I-beam is, you'd want to use the area. And that's going to be that chunk of area, this distance, and you're going to square that distance. The farther away that area is, the bigger that number is, and that's going to help you get a larger number for your strength of whatever you're doing. So very similar here, but I always do this drawing, is if you have a door, you're going to apply a force on the doorknob, and it's a distance away. And I'm going to say this is, so this is moment. This is the moment of a force. So we have moment, which is force times distance. I'm going to say it's a moment of a force, and I'm going to say it's the first moment of a force, because we're just multiplying by the distance. And then when we have this I term, is like, hey, we have some sort of, it's a little bit different, where we have some sort of mass away from this distance, and this I term is like, hey, we have a mass, and then we're going to take the distance squared. So just like moment is a force times distance, and we're calling it the first moment of force, moment of inertia is mass times distance squared. So I'm going to say it's the second moment of mass. So that's how you would say that, second moment. It's just because this term is squared. And hell yeah. And then so now you can just think of that, hey, first moment of whatever, it's just kind of this times that. But second moment, no, it must be a quantity where we have to multiply, we're squaring one of the terms. And we're doing so because, hey, that pops up right there. You know what I mean? We just did it. We just said that the sum of the torques was equal to the force times the distance, which is the mass times the acceleration times the distance. But because of continuity, because this thing spins, you know, at the same rate, you know, being a rigid structure, the angular acceleration of both these terms are going to be the same. And the opposite is also true. Because this thing spins like this chunk's hardly moving, this one's moving hella. So you could say that the acceleration of A is not the acceleration. I mean, the acceleration of this 1 is not the acceleration of 2. So I'm just going to say this is 1 and this is 2. And so then we have to use that equation for what is angular acceleration. Well, it's angular acceleration times the distance is going to be that normal acceleration. So that's where we get this term, and you get md squared. So that's where you just get I1 alpha plus I2 alpha. And then we can see that sum of the torques is equal to the sum of the moment of inertia times alpha. And alpha won't change for a rigid body. So I'm sorry, I'm just learning on the fly, but hell yeah, these summation terms, like obviously, yes, the sum of the torques is equal to the sum of the moment of inertias. If you are going to sum the moment of inertias, but typically you'll just do sum of the torques times I alpha, because you're just going to look up this term from charts. But that's where, I'm going to go a step farther and then actually get it as a chunk of mass. This is your simplest. If I have a chunk of mass, it's a distance away. Hey, I know the second moment of mass for this. It's md squared. Okay, sweet. And so let's continue on with this one where, in 1 second, let's say it falls and this goes 6 meters. And this is the actual distance it will go. If this one falls 6, is that right? We'll figure it out. Oh, well, and then the other way that we could do it, we'll do 2 problems in one. Let's just say we don't know the distance it's going to fall, and so we're going to say this is x, but because we have 3 segments, this one's going to fall 3x. And so now let's write our equation again. We have the sum of the torques. We found that that's 1/2 mgl. And that's going to equal to this side, which is mass times the acceleration of this one times the distance to that one, plus the mass times the acceleration of this one times the distance to that one. But we know from kinematics that this is always one that I do, is if you have something dropping off a cliff, velocity is 0. In 1 second, the velocity is going to be 10 because the acceleration is 10 meters per second per second. Cool. And so we get an average velocity of 5 meters per second. Over that 1 second means that this thing dropped 5 meters. So the distance in 1 second that it's going to drop is 5, and this is related to the acceleration by a factor of 2. So if I want to know if I want to know the distance, if I want to get acceleration in terms of acceleration as a function of distance, well, let's just see what I do here. If I know my distance is 5 meters, I would multiply 2 by 2 to get my acceleration. Okay, hell yeah. And so this is what we don't know, is the fall distance of that one. So we're going to say that x times 2 is equal to a, or just 2x is equal to a. And so we're going to plug that into right there. And we know that this is going to be... so we knew that this distance was x, and then we had to multiply by 2 to get the acceleration. This distance is 3x. We still have to multiply by 2, so we're going to have 3x times 2 to get that acceleration of this term. Alright, so let's do it. So we have mass times 2x times d1, which is 1/4 L. And then we have this term, mass times, I'm just going to do 6x times 3/4 L. Alright, so, and then right here, we can solve for what x is. But now, let's go back over to this one, because this will probably be just a little bit easier. So we have 1/2 mgl is equal to mass times the acceleration, and then this is the distance to here. We have L divided by 4, so that's going to be L squared divided by 16 plus, and then we have mass times the angular acceleration, and the distance to this one is going to be 3/4 L. When we square that, we're going to get 9/16 L squared. So we're going to get 9/16 L squared. Okay, so right here, we're going to have 1/16 plus 9/16. Everything is else the same, so we're going to have 10/16 alpha L squared is equal to 1/2 mgl. And then we can kind of simplify this. Oh, and I feel like, did I do it right? Nope. I've been doing these a lot, but no, this mass has to be a half. So we're saying, yeah, 1/2 is the mass right here, times gravity is the force, times that distance. And so when we come over here, when we're summing these up, this mass is just 1/2 m. So there you go, 1/2 m, 1/2 m. Alright, so there should be a 1/2 in here. Sorry about that. And now, so we have a 1/2. So here we can simplify by canceling the 1/2s. We can cancel an L. Oh, and there should be a mass right here. So sorry, 1/2 m. So we can cancel in mass. And so we're going to have G is equal to 10/16 alpha, and then just one of these L's, because one got canceled. Alright, so we have alpha is equal to, now I'm just going to solve for alpha. So I'm going to be 16/10 G divided by L. And this is going to be 1.6. So we have 1.6 G divided by L. Alright, sweet. So, and let's use this term, because if this is my angular acceleration, maybe I wanted to find the acceleration at this L divided by 4. And what do we know about angular acceleration? We say angular acceleration times the distance is just the acceleration at that point. Cool. So I'm going to say I want angular acceleration times L divided by 4. That's going to be 1.6 G divided by L, and now multiplied by L divided by 4. The L's cancel, and I'm going to get 1.6 divided by 4, and I'm going to get 0.4 G. That's going to be my acceleration, 0.4 G right there. And so if that's my acceleration at that point, in 1 second, my distance is going to be, just like if I drop off a cliff and my acceleration is 10. After 1 second, my position is going to be 5. So if this is my acceleration at that point, alright, so my distance at that point is going to be 0.2 G. Cool, so hopefully that's kind of what we find here. So, man, we're not doing good with space trying to do two problems at the same time. But let's solve for x over here. So we have we can cancel out an m, we can cancel out an L, and we're going to have 1/2 G is equal to, and this is going to be 1/2 x plus, and this is going to be let's say 3/2 times 3 is going to be 9/2 plus 9/2 x. So cool, we're going to have 10/2 x. So we have 1/2 G is equal to 10/2 x. Oh, I feel like we messed something up here too. Oh, yeah. Did I not do my mass? Yeah, my mass has to be 1/2. Holy Toledo. Yep, so sorry I messed that up. Yeah, so the sum of the torques has to equal, the contribution of that mass. And so we can factor out a 1/2. So we're going to have G is equal to 1/2 x plus, I swear we just get the same thing. All right, let's slow down on that one. Oh man, we're just making a mess. But anyway, so we have the sum of the torques is going to be 1/2 mgl. That's summing both these up. So we already did that over here, and that's going to equal to this equation mass A1 times D1 plus mass A2 times D2. And we know that the acceleration is going to be mass 2 times the position that it's going to fall times D1 plus mass 2 times the position at 2 times D2. And we know this mass is 1/2, so we just have 1/2 m. Cool. And so we're going to have 1/2 m 2x times this distance is 1/4 L plus 1/2 m times 2. Now this distance is going to be 3x, so we have 3 times x, and then this distance is going to be 3/4 L. So yeah, what did I mess up? I think we're good. So we have 1/2 mgl. Now we're just solving for x, and I might have. And what were we hoping x is? Oh yeah, no duh. So x is 0.2 times 10. Yeah, x should be 2 meters, and that's kind of what we set up. So let's see if we actually get that. I'm sure we did. I got a little bit freaked out. All right, so how do you want to simplify? I just want to get rid of the halves, get rid of the masses, and get rid of the lengths. Sweet. So we're going to have g is equal to, now right here we're going to have 2 divided by 4. So we're going to have 1/2 x plus, yeah, we're going to get the same thing. So now we have the 2 and the 4 make a half times 9. So we have 9/2. 9/2 x. Yeah, so g is going to be 10/2 x. Yeah, no duh. So x is going to be 2/10 g, and that's going to be 0.2 g. All right, sweet. But that's kind of doing it both ways, and maybe I should make another video and make it not so sloppy as. But this is just good for me, I guess. What else? What else can we? Yeah, so we did it kind of both ways, and we figured. We kind of know what the continuity is. And yeah, so then if we know that distance is going to be 0.2 g, we can use our equation for angular acceleration is going to be, or angular acceleration times the radius is the acceleration at that point. And we know the acceleration at that point is going to be 2 times this distance. So we're going to have 0.4 g is equal to the angular acceleration at that point. And this r is going to be alpha d is equal to 0.4 g. So that d is going to be, so we have, is going to be 1/4 L times 0.4 g. And to solve for this angular acceleration, we're going to have 4 times 0.4 g divided by L. So that's going to be that 1.6 g divided by L. So yeah, cool. Just another way to get there. All right, hell yeah. So now with this equation, we have alpha is equal to 1.6 g divided by L. So now let's use it. Let's find so what we want to do is we find the acceleration at the center of mass. That's going to be at a distance of L2. So we know that angular acceleration times the radius is the tangential acceleration, and that's what we want. So we're going to say that acceleration is going to be this 1.6 g divided by L, and then the distance to the center of mass is L divided by 2. So sweet. So we're going to have, that's going to be 0.8 g. L's cancel, and we're going to get 0.8 g. Now and that's just with 2 masses. If you do this problem, you'll get 0.75 g. So with the bar being what it is, you're going to get an acceleration here of 1.5 g, and you're going to get an acceleration of the center of mass of 0.75 g. And doesn't that make sense? If this point accelerates by 1.5, this point accelerates by 0, just using similar triangles, the midpoint is going to accelerate by 0.75 g. But that goes against my misconception that if I drop this bar, the center of mass will fall with an acceleration of gravity. But when it's hinged, it's not going to fall with an acceleration of gravity. So then my question was why? And then let's just explore that kind of from F equals ma. So we have F equals ma, and we're going to sum the forces kind of just in this general vertical direction. So we sum the forces is equal to mass times acceleration. Now the forces in this direction are going to be 1/2 mg plus 1/2 mg. So that's going to, and we're going to call that the positive direction because that's going to be positive motion. So we have a total force of mg. But now I say that we're going to have a force right here at O. So I'm just going to call this point A, and we have a force, that force A, whatever. So we're going to say mg, and then we're just going to say minus A is equal to the mass times acceleration. And this is going to be the center of mass, right? So we're going to have the mass is going to be m. The acceleration of the center of mass is going to be 0.8 g. So now if we solve for A, we're going to get A to this side and then this to that side. So A is going to be 1 mg minus 0.8 mg. And we can see that that force right there is going to be 0.2 mg. So it's going to be 20%. In this generic, if we have two chunks of mass connected with a massless rod, that's going to be the force right there. But when we have the total rod, this will go to 25%. Alright, hell yeah. And this video might just be more for me, but it helps my misconceptions of what torque is and how torque causes motion. And then if you do have torque, you absolutely need, if this bar was just moving this way, and then all of a sudden it starts to rotate, the only way you can get something to rotate is to apply a torque on it. And if you have just only forces in one direction, a torque has to be another force in an opposing direction that causes a couple. And yeah, so that's fascinating. Even if you put a force directly this way or that way, that would not cause any rotation. So it has to be an opposite. So yeah, this is fascinating. This is the learning moments even just for me. So hopefully it shows, because yeah, it's just like that's the difference. Why it's just like if I just let go at this pivot, it's just like, well, why doesn't the center of mass fall at the same speed? Is because it is on a pivot. It has to swing, and if it has to rotate, then it has to have a torque to make it rotate. And if the only driving forces are in the vertical direction due to gravity, to cause something to rotate, you must have to apply this upward force. You know what I mean? So yeah, so I'm going to be looking for that when it comes to things that are torqued. Is like, yeah, if you just have forces in one direction, you're just going to get motion in that direction. But if you have something that's rotating, it can only rotate if you have applied and this is super cool. No, this is really good, because I was so confused. Like if you have, like let's say this, if this is just an object floating, if this object is floating in deep space where there's nothing around, this is the only object in the universe, and then you go to apply a force right there, this object will now be right there, and it will not spin. Thank goodness. So even though this was such a scrappy way, like I'll try to clean it up if I get motivated. That's the thing. I just don't get motivated to make clean work. You know what I mean? But yeah, because you can come up with such good understandings. you know, just from the nitty gritty, you know what I mean? Because I was so confused about this. Because this is breaking two misconceptions. My conception is that if you had a chunk of mass that was just floating there in space, and I go apply, and it's not moving at all, so it's not spinning, it's not moving that way or that way, and I apply a force at the end right here, that just by the fact that it has mass, I thought, and maybe this is still a misconception, but now is like, hey, there is no force going this way, because we don't have stars or Earths or planets, you know, that are trying to attract this mass, you know, in a certain direction, or if I do apply this force, it actually wants to go that way, where you'd get opposing forces, and then you would get a torque. But no, I think if this is just floating in outer space, you put a force over there, it's just going to move that way, which is very mysterious to me. And I still do not know if I'm making that, if I'm saying that right. Like, even as is, if I have this chunk of mass, this bar in outer space, and I go push on it, is it going to and can't you like, and the other thing, isn't it within reference frames? Like, if I had a plank of wood, if you were skydiving, and you're skydiving with a plank of wood, and you got both falling at the same time, and then you go apply a force right here, just a force of your hand, isn't this thing not going to rotate? Because there's or is the center of mass, the force acting at the center of mass, is that are you applying a torque right here where you're not applying the same force over there? So yeah, I guess I just leave it with that I'm still kind of confused. But from this perspective, if I have forces in this downward direction that are going to make the center of mass go that way, well, it's not going to be like free fall, because it's not falling in translation, it's rotating. And if it's going to rotate, the only thing that can cause that to rotate is a torque, and you need another force to cause that torque, and that force is right there. All right, so I'm glad I talked through this and kind of made like, no, I don't think this is right. Because if you apply a force right here, and then you sum the moments from this point, like point B, this is point A, then you are going to have a unbalanced torque. So this thing is still going to spin that way. Yeah, that's fascinating. Oh, you know what though? Yeah, this is so interesting. So it's still in this case, there is no other force over here that's going to impede the center of mass from moving this way. So it's still, just like I have a 1 kilogram mass and I apply a 1 Newton force, in 1 second, this mass is going to go from 0 meters per second to 1 meter per second. Well, the same thing here. If this is in deep space, I apply a 1 Newton force. This whole bar is a mass of 1 kilogram. This center is stationary. In 1 second, the center of mass will have a velocity of 1 meter per second. It's just the fact that if this is, it'll also cause a torque, but the only way to you know, and then the only way to get this to there and then have this higher is to have this, what is it? This point doesn't move? Yeah, that's the other thing. Yeah, this point, this point will move this way. Oh man, this is bizarred me out. But these are good questions for me to ask, you know, and make further videos on, because it is just kind of interesting. Because some of the forces in this direction would say that we applied a force and there's no other forces in this direction, so the center of mass will be up there. But we do have rotation, Yeah, maybe that's not true either. Anyway, I got to explore that. So I'm going to end it there. So thanks for joining me. And guess what? That's a video.